Hi, I'm Kazra Jamshidi from Simon Fraser University, and I'm going to present Anti-Vertex for neighborhood constraints in subgraph queries. As networked and graph data are becoming increasingly ubiquitous, graph databases are also growing in popularity. These databases allow users to query a large data graph to retrieve interesting and meaningful subgraphs using specialized graph query languages that have been developed recently. These languages typically incorporate a declarative pattern-matching syntax, which allows easily expressing query graphs, as well as SQL-inspired constructs for aggregation and filtering. Cypher is a popular graph query language, and its pattern-matching syntax looks like this. The match clause encodes the structure and labeling of the query graph, filtering out subgraphs like this one, which has incorrect labeling, but allowing subgraphs like this one, which match the query graph structure and labeling perfectly. There are additional filters in the where clause that must also be satisfied. Here, the author represented by the blue vertex must be younger than 30. This example used the graph schema to filter matches, but in our work, we're interested in constraining the neighborhoods of matching subgraphs. As we're going to see, this is going to be difficult, so let's take a look at a motivating use case, anomaly detection. Consider this database, where vertices represent schools, businesses, and fire hydrants, and two vertices are adjacent if they're nearby. A regulation has been updated to require nearby schools and businesses to have access to 3 nearby fire hydrants, where previously only 2 were required. We want to find all of the non-compliant cases like Hogwarts and KFC, without manually sifting through the compliant cases like Luke's and Chilton. A simple solution is to look for all of the cases where the old regulation was met strictly, exactly 2 fire hydrants, but not 3. We can translate this logic into a quick Cypher query. The initial match clause finds all vertices which complied with the old regulation. Then those same variables are used in the subquery to filter those vertices which comply with the new regulation as well. Finally, the remaining vertices which are not compliant are returned. Note how the pattern in the initial match clause had to be repeated in the subquery, and imagine how much more repetition would be required if the query graph were larger or if there were additional filters. It's also difficult to recognize the intent of the query. We can avoid this repetition if we refactor. Now, the initial match clause and the subquery are distinct, but notice the additional filters in the subquery, which are required to ensure correct semantics. The filters are simple in this case, but they required expert knowledge to write, and they can become increasingly complex as queries grow. What's worse, errors can be silent. Without the E not equal to C filter, the fire hydrant bound to the variable E will also be bound to the variable C, and so no results will ever materialize, which can be difficult to diagnose as a bug. Finally, updating or adjusting such a query is challenging. Other filters necessary to satisfy unrelated requirements will be mixed in with those for the neighborhood constraint, and updates to the initial match clause will require corresponding updates to the subquery. These factors make it difficult to maintain this query over time as requirements change. To address all of these issues, we propose the Anti-Vertex construct, which enables users to directly express constraints on vertex neighborhoods. Using Anti-Vertex, we get a much simpler query. Here, a vertex is marked with an exclamation point to indicate that it's an anti-vertex and it should not be matched. Any subgraph which can match this anti-vertex is going to be filtered out. For example, suppose we bind Luke's and Chilton to A and B, and fire hydrants 1 and 2 to C and D. Then, since E can be bound to fire hydrant 3, the subgraph is rejected. Now, adding or removing other patterns in the match clause won't affect the anti-vertex, and other filters and subqueries aren't going to be mixed in with the neighborhood constraint. So with this motivation in hand, we're ready to formally define the semantics of anti-vertex to ensure consistent understanding and enable automation in database engines. Additionally, these semantics are language agnostic and they can be implemented in any graph query language. I'm going to provide a streamlined explanation of the semantics in the 3 subgraph querying paradigms that are widely supported: homomorphism, no repeated edge, and isomorphism. First, I have to explain some notation. Then I'll explain each querying paradigm and how anti-vertex semantics fit in. So, let's say we have a data graph G and a query graph Q. For each vertex in G, we're going to define something called an EU neighborhood. The EU neighborhood of a data graph V, data vertex V, is the set of vertices that match U and that have an edge to V which matches E. So in this example, the data edge PS is mapped to the query edge E1. So the E2B neighborhood of P is all of P's neighbors which match B. B is yellow, and E2 has no label, so this neighborhood consists of P's yellow neighbors, Q and R. Likewise, the E3B neighborhood of S is all of its yellow neighbors as well. To make the neighborhood constraints explicit, we're going to mark a set of vertices in Q as anti-vertices, denoted by VQ-. These should never be matched. The set of remaining vertices, which we call true vertices, are VQ+. Pictorially, we depict anti-vertices with dashed borders to distinguish them from true vertices. This visual language is helpful during analysis, programming, and debugging to visualize the exact structural constraints that are being applied. So a data subgraph is going to count as a match for the query graph if 1, it correctly matches all of the true vertices and the edges between them, and 2, it can't be matched to any, or it can't be extended to match any anti-vertex. To make point 2 more precise, we're going to define a function C of U that gives all of the data vertices that could be correctly matched to a vertex U in the query. Basically, C of U gives candidates for extending the subgraph. Now we can rewrite to say C of U bar must be empty for every anti-vertex in the query. The definition of C is going to depend on the underlying matching paradigm, so that's what we're going to look at next. Homomorphism matching semantics are the simplest of the three, and require only that each edge in the query graph has a corresponding edge in the data subgraph. In this example, we can begin by mapping the AB edge to E1, then the AC edge to E2, and finally the BD edge to E3 in order to obtain a match. Homomorphism semantics also allow vertices to repeat in a match, such as this match where both C and D are mapped to the data vertex S. Finally, edges are also allowed to repeat, like in this match where both AB and AC are mapped to E1. This translates to the following definition of C. For example, let's say that we add this anti-vertex U bar as a neighbor of D. In all of these matches, D is mapped to S. So we need to look at the neighborhood of S to make sure that there are no possible matches for U bar. Since neither U bar nor the edge to it have labels, C of U bar is simply S's entire neighborhood. Since S has a non-empty neighborhood, of course, all three matches get filtered. But if we were to add more edges, now C of U bar becomes the intersection of adjacency lists of the matches for A, C, and D. In this last match, we get the intersection of P, Q, and S, which is empty. While in this match, P and S do have a neighbor in common, Q, so it's filtered. No repeated edge matching semantics additionally require that the matching subgraph has a one-to-one mapping of edges, though vertices can repeat. This match under homomorphism semantics is not valid here because E1 is repeated. Looking at the definition of C for no repeated edge, the only difference from homomorphism is that previously matched edges to U bar are removed. Once again attaching an anti-vertex to D, Q is removed because the E3 edge has already been used. If we add more edges to U bar, neither match will be filtered. In the second match, C of U bar is empty since E3 has already been matched and so Q gets removed, while in the first match, C of U bar is empty because P, R, and S have no common neighbors. Isomorphism matching semantics are even stricter than no repeated edge, and do not allow repeated vertices either, invalidating this subgraph where S repeats. This manifests in the definition of C by simply removing all previously matched vertices. Now, if we add U bar back, C of U bar is empty because the neighbors of S are already present in the match. If we add a new neighbor of S in the data graph though, then C of U bar will be non-empty and this match will be filtered. Using these formal semantics, the anti-vertex construct can be added to any graph query language that has declarative pattern matching syntax. In Cypher and PGQL, there's the match clause, and Gremlin has a .match operator, and so on. To demonstrate, we're going to enhance the Cypher grammar to support anti-vertex by marking a vertex with an exclamation point, which is the not operator in many programming languages. We need only change the pattern matching grammar, leaving the rest of the language unchanged. The highlighted portions here represent the new fragments that we've added to the grammar. In addition to the true vertex defined by node pattern, there is now also an anti-vertex marked with an exclamation point, defined by anti-node pattern. Anti-node pattern only occurs in pattern plus, either on its own or in mutual recursion with pattern O. Meanwhile, pattern O allows pattern plus at the end of a relation with a true vertex, or in the beginning of a recursive relation with itself. Basically, the anti-vertex can occur in the beginning, middle, or end of a pattern. So this enhanced grammar allows cases like the following. Two true vertices A and C, adjacent to an anti-vertex B, or two anti-vertices A and C, adjacent to a vertex B. But it does not allow a sole anti-vertex or an anti-vertex on both ends of a relation, like this. Our semantics make this query ill-formed, since neither variable should be matched. We're currently working on generalizing the semantics to allow for such anti-patterns. This grammar does allow length-specified patterns which involve an anti-vertex. Here, we have an anti-vertex, and then a two-hop path, and then a true vertex. However, it's unclear whether the intermediate vertices in these paths should be anti-vertices. And it's possible that given semantics for anti-patterns, there can be ambiguity in programmer intent with length-specified patterns involving an anti-vertex. To maintain flexibility for future proposals, we developed a second grammar which explicitly disallows length-specified patterns involving an anti-vertex. The paper shows the full set of changes and a detailed explanation. Unfortunately, I don't have time to go into it here. To build intuition for anti-vertex semantics, the paper shows a suite of examples highlighting different cases in isomorphism and no-repeated edge semantics. Let's take a look at one of these examples in a social network setting. Here, vertices represent people and there are two edge labels, following and liking. A query edge with no label indicates that the edge is unconstrained. A data edge with any label can be mapped to it. These are the matches in isomorphism and no-repeated edge semantics. Let's quickly check them. The PQ edge is certainly a match in isomorphism semantics, since Q's only in-neighbor is P. On the other hand, the second PQ edge can match the anti-vertex, so this is not a match in no-repeated edge semantics. P and S is a match in both paradigms, since S only has one incoming edge. And finally, SR is not a match in either paradigm, since R has two incoming edges. Be sure to check out the other examples in the paper. We also show how anti-vertex interacts with the symmetry breaking optimization that's employed by some query engines which use isomorphism semantics. Symmetry breaking prunes out automorphic matches, which are distinct matches containing the exact same of data vertices. You can see here that Q and R swap roles in these two matches. This occurs when the query has symmetric vertices, in this case B and C. One of these matches can be pruned by enforcing constraints on the variables, i.e. breaking the symmetry. Now, if an anti-vertex is added, which filters this first match, B and C are no longer symmetric, and hence the second match is not filtered. If B and C both have an identical anti-vertex, then they once again become symmetric, and in this case, there would be no matches. To conclude, as graph datasets are becoming increasingly rich and analysts are working to answer increasingly difficult problems, we require higher-level abstractions so that we can develop maintainable subgraph queries. In this work, we developed the concept, intuition, and semantics for the anti-vertex. The anti-vertex is a huge step towards simplifying the expression of neighborhood constraints in subgraph queries declaratively, without repetition, tedium, or knowledge of underlying semantics. As a result, neighborhood constraints are not only simpler to write using anti-vertices, but they're also easier to maintain and debug. We're currently working on generalizations of the anti-vertex concept to edges where both endpoints are anti-vertices, paths containing such edges, and even graphs comprised of multiple such edges and paths. These higher-order neighborhood constraints provide even richer abstractions in order to facilitate more complex analysis and make increasingly complicated queries easier to express declaratively. We're also excited about opportunities for automatic optimizations since the user no longer has to manually handle matching semantics. I'd like to thank you for listening to this talk and invite you to feel free to contact us if you want to know more or to contribute to future projects. Have a nice day.